Hey, what's going on, everybody? We're going to be studying the binomial distribution today, and this has to do with random variables. What we're going to be doing particularly is calculating probabilities for when random variables are binomially distributed. And I'll explain to you what it means for a random variable to be binomially distributed. We're going to look at three examples here, starting with this one, and it's going to be their first exposure to a binomial distribution. It says, suppose a three-digit number is created by randomly drawing numbers from a container holding 7 ones and 3 other numbers. And then I added in with replacement. I want each digit that we're trying to make in this random number to have the same probability of having a 1 as of not having a 1. And what we're going to do then is calculate what the probability is that the number would have 2 1s. Okay. Well, this experiment meets the first criterion for having what we call a binomial distribution. Whenever you're working with a binomial distribution, an essential element of that binomial distribution is that there's only 2 outcomes for your random variable. Okay? Now, a random variable here is the number of 1s that we get, right? And, well, you either get a 1 or you don't get a 1. There's only 2 possibilities. So, 2 outcomes are always part of a binomial distribution. That's why it's a binomial distribution. And we classify those outcomes as a success or a failure. That's just a generalization, really. And it makes it much easier to do probabilities with binomial distributions. All right, success or failure is all we care about there. All right, now let's reason this out. Whenever we're looking at this situation, we know the probability that you get a 1 on any particular draw is 7/10, and the probability that you don't get a 1 then would be the remaining 3/10, right? Okay, so we only have a success or a failure. The successes and failures together make up 100% of your sample space, so those probabilities add up to 1. Now, how are we going to find out the probability then of getting the 2 1s in this number? Well, there's 3 situations that could work here. We could get 1 1 and not 1. Okay, so 1's the first 2 times. But it's possible that we could get a 1 the first time, not a 1 the second time, and get a 1 the third time. Or it's possible that we don't get a 1 the first time, but we get a 1 the second and the third time. Does that make sense? There's 3 outcomes which match the qualifications that we're looking for here. And then how do we calculate the probability of each of those? Well, we're just going to multiply the probabilities. If you could visualize a tree diagram here, we're going to multiply the probability of getting a 1 with the probability of getting a 1 with the probability of not getting a 1. Since these are independent probabilities, each draw, we can't just multiply them together. So 7/10 times 7/10 times 3/10. That would be the probability of getting a 1 the first 2 times, and then not a 1 the third time. All right? And then in our second possibility here, 7/10 chance of getting a 1 the first time, 3/10 chance of getting 1 the second time, and 7/10 chance the third time. And then for the last of our possible outcomes here, its probability is going to be 3/10 times 7/10 times 7/10. Now, what do you notice about those 3 outcomes? Don't they all have exactly the same probability? All right? And every time you have a binomial outcome, if you're looking for a specific number of successes, then you're always going to have the same probability. All right? Now, the same number of successes and failures, I should say. So I'm here having 2 successes and 1 failure every time. Now, I could have generalized that to say that there were 3 possible outcomes that fit the description, and that I was going to have 2 successes, so I was going to have to multiply 7/10 by itself twice. All right, so 7/10 squared. And I was going to have 1 failure, So multiply times 3/10 to the first power. Okay, and then that turns out to be 441 out of 1,000. All right, now we'll kind of take this a little bit further in the next example, but I want to talk a little bit more about what's included in a binomial distribution. I've already said that in a binomial distribution, you're going to have two outcomes which you can classify as success or failure. But there are some other very important elements to a binomial distribution. One of those other elements is that you have to have a fixed number of trials. Okay, a fixed number of trials. Now notice here, we had a 3-digit number, so we were choosing a digit 3 times. All right, so fixed number of trials was part of this experiment. Super important. Also, you have to have the same probability of success in each trial. Now, that's why I put this little bit in here about us drawing numbers and replacing the number every time. All right, you got the same probability of success in each trial. And then finally, and this is kind of related to that, each trial needs to be independent. If you had those 4 qualities for a random variable, then that random variable is binomial distributed. All right, each trial independent. Very good. All right, now I want to take this same problem and go to the next level with this sort of. Instead of creating a 3-digit number using the method described, let's say we want to create an 8-digit number. Now, it can get a little bit ridiculous trying to use a tree diagram, for instance, whenever you are choosing something 8 times in this case. All right, you don't really want to do that. And so we would like a formula that's going to help us find out what this probability is without having to use a tree diagram or other methods. Now, hopefully you picked up a little bit on the basics for what we're doing in the previous slide. For instance, if we're trying to create an 8-digit number that has 6 ones, and then that would imply that the other 2 are not ones, well, we're going to have to multiply by the probability of getting a 1 6 times, right? And since then we would have 2 digits that were not a 1, we'd have to multiply that probability twice. Now, 7/10 to the 6th power times 3/10 to the 2nd power would be the probability of any particular outcome in which you get 6 ones and 2 zeros. The next thing we need to know is how many of those outcomes are there. All right, well, here's how that's going to work. We have 8 digits to choose from, right? We're going to have 8 trials here, and we want 6 successes. You guys remember your combinations whenever you're learning the binomial theorem back in chapter 6? All right, this right here will tell me how many ways there are of getting 6 successes in 8 trials. All right, now just a little side note. In the previous example, we had 3 digits, 3 trials, and we were trying to get 2 successes, and it turns out that 3 choose 2, or 3C2, as you might know it, is equal to 3. That told us there are 3 ways in which we could get that digit, the 3-digit number with 2 ones, all right? So that was just relating to what we just did. Here, we're trying to get an 8-digit number that has 6 ones in it, so 6 successes. All right, now just to make this a little bit neater, I'm going to say that we're finding the probability that a random variable x is equal to 6, where that random variable represents the number of successes that you have, essentially. All right, so we're looking for the probability that we have 6 successes in this trial. Now, as far as calculating the value of 8C6 right there, you might remember that you can use a certain formula. All right, I'm going to write this off to the side. If you have n items and you're trying to choose r items, trying to figure out how many different ways you can choose r items out of those n items, then you can find out that number of combinations by taking n factorial and dividing by the product of r factorial and n minus r factorial. Okay, and remember also you could say that that was NCR. That was another way of writing that same notation. And that's kind of important for whenever you're using a calculator to figure this thing out. Right now, let's go ahead and do this without the use of the calculator if we can. All right, so 8 choose 6 right here, or 8C6 would be equal to 8 factorial all right, that's our n over 6 factorial, that's our r, times n minus r, 8 minus 6 is 2, 2 factorial, and then times 7/10 to the 6th power, times 3/10 to the 2nd power. And remember the way you simplify this formula right here, you have in the numerator 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Here you have a 6 times 5 times 4 times 3 times 2 times 1. You can do a little canceling, can't you? You can cancel out that 6 factorial with the 8 factorial, and it will leave you with 8 times 7 in the numerator. All right? So we have 8 times 7 over 2 times 1. That's 56 over 2, or 28. All right, so there were 28 different combinations of 8-digit numbers that we could make that would contain 6 ones. That's what that tells me. And so we'll multiply that then by the probability of getting 6 ones, 7/10 to the 6th power, and then times the probability of getting not a 1 twice. All right, now use your calculator for this. And when you do so, if you'll go ahead and round this answer to 3 significant figures, you find out that the probability that you would get those 6 ones is about 0.296. 29.6% of the time you would make that happen. Okay, so that was using binomial distribution again. Now, let's generalize here. If we have a random variable that is binomial distributed, meaning, as we said earlier, there's only 2 outcomes, there's a fixed number of trials, each trial is independent, and the probability of success is the same in every trial, then you can find the probability that the number of successes, that's what the random variable would represent, that the number of successes equals some number r by using this formula here. You need to write this down. All right, n is the number of trials, r is the number of successes that you're looking for, and what you're going to do is you're going to multiply by the probability of success, which we'll call p, to the r power. And if you have r successes, every other trial is going to give you a failure, and you would find out how many trials were remaining if you subtract the total number of trials by the number of successes. And so that would be n minus r. Now, I'm going to need to do one more thing here. Also, the probability of failure would have to be 1 minus the probability of success, wouldn't it? All right. Now, in this instance, we already said n is the number of trials. R is the number of successes. And P is the probability of success. All right, you should have an idea now of how you find the probability of a binomial distribution. We're going to work with a couple more examples here, and I do want us to use our calculator the rest of the way to accomplish things. Let's look at this. It says a school physics team builds a water balloon launcher that hits its target 80% of the time. They are given 5 tosses in a competition. We're going to let X represent the number of hits, the number of successes, and we want to find, first of all, the probability that they hit the target essentially every time. Okay, well, using our formula then, that would have to be equal to this. All right, there's 5 trials, and we're looking for 5 successes, so we'll do 5C5 times the probability of success is 80%, so 0.8 to the 5th power because we want 5 successes. Now we also have to multiply times the probability of the failure, which would be 0.2 the other 20% of the time. And we need that to go to the power of how many failures we're going to have. Now in this case, we're not going to have any failures, are we? Because we're going to have to target all 5 times. All right, now on your calculator, you're trying to figure out what 5C5 is, times 0.8 to the 5th power, times 0.2 to the 0 power. Go for it. All right, and you do that to 3 significant figures, you end up with 0.328 being that probability. 32.8% of the time, they would get a hit every time. All right, for their little competition. Well, let's say we wanted to find the probability that they are not perfect, but that they get at least 3 hits on the target. Well, what I'm wanting to do with this example is just make sure that you understand everything that's in your sample space. If we're trying to find the probability that the number of hits is at least 3, we need to include the scenario where the probability of getting 4 hits is included, and we need to add with that the probability of getting 5 hits, don't we? All right, now the probability of getting 4 hits, well, we have 5 trials, we're looking for 4 successes, we're going to multiply that by 0.8 to the 4th power because we want 4 successes, times 0.2 to the 1st power because we want 1 failure. And then we've already figured out that this is, well, the more exact value is 0.32768, right? We don't need to recalculate that. We figured out earlier in the problem. Okay, now use your calculator, figure out what the probability of getting 4 hits is, and then add it with the probability of getting 5 hits. Now this sounds like a pretty decent success rate for this physics team here. About 73.7% of the time, 0.737, they're going to hit 4 or 5 targets. They're going to hit the target 4 or 5 out of 5 times. All right, one more question here. Let's say we want to find the probability that they hit the target at least once. All right? Now, if we're going to do that the way that I just showed you a moment ago, we'd have to find out what's the probability that they get 1 hit, plus the probability that they get 2 hits, plus 3 hits, plus 4 hits, plus 5 hits. That would be a whole lot of probabilities to find. Sometimes we want to use the complement of the event in order to find the probability of an event. And the complement of hitting the target at least once is that you don't hit it at all. All right, either you hit it or you don't, right? And it turns out that the probability that we hit it at least once would be equal to 1 minus the probability that x is not greater than or equal to 1. Or, in other words, it's equal to 1 minus the probability that the number of hits is equal to 0. Now, that's going to be a little bit easier to calculate than had we tried to take all 5 of the other possibilities and add them together. All right, so we're going to get 1 minus 5C0, right? We're having 0 successes this time, times 0.8 to the 0 power, again, 0 successes, times 0.2 to the 5th power, because, well, 5 failures, right? And follow through with your GDC, figure out what that is. Now this is a really high percentage right here. It was about 1.00 if you round to 3 significant figures. It wasn't exactly 100%, but close enough that we can call it a 100% chance, essentially, that this physics team is going to hit the target at least once out of its 5 attempts. All right, you know now how to calculate the probability of an event when it is binomially distributed. All right, we'll talk a little bit more about this because there's more notation for you to learn and so forth. But you've got, and there's calculator stuff for you to learn, but you've got the basics for it. All right, thanks for your attention. See you next time, guys.